an object of mass m rests in the horizontal plane. The angle theta that the plane makes with the horizontal is slowly increased from 0 when theta is equal to theta 0. So this theta 0 would actually be theta sub 0, right? This object needs to slide. What are the coefficient of static friction and the normal reaction force n of the plane at this angle? So when it starts to slide, right? Well, okay, so you have several options. You have the coefficient of static friction. This should also be mu's. They got cut off, right? These are all the coefficient of static frictions. N's are the normal forces. So if you draw these, you're going to have the object. You're going to have the gravitational force downwards. Gravitational force is equal to mg, right? So you have an angle, and this angle is going to be theta. Of course, we're going to see the angle or use the angle where it starts to move. So we're going to make this theta 0, and now we should probably find what the normal force is and what the parallel force is. So I'm going to move this equation to the bottom, and in its place I'm going to write two vectors, one that is perpendicular to the surface, right? And this is going to be same as the reaction force, same size, right? And the second one is going to be parallel to the surface in green. And let's make the angle here theta. Therefore, this R, which is also going to be the reaction force here, would be, let's not change the convention. Let's put this as the force that is perpendicular, so FP, perpendicular to the surface, and this is going to be mg equals theta, right? The force that is parallel in green actually does parallel as well. So let's make these signs parallel and perpendicular, like so. The parallel force is going to be mg sine theta, right? We want to know the force of friction. Force of friction. Well, it says that at this angle it just barely starts to move, right? So it means that the force of static friction at this point must be equal to this parallel force, mg sine theta, right? They're just barely equal, so that at this point, at this angle, this mg sine theta is just beginning to become equal. If you increase the angle more, this becomes larger, right? The second equation for friction was, we know it depended on the coefficient of static friction times the normal reaction force, R, right? This R, we're going to change with mg cosine theta. Mg cos theta, like so. And we're almost there. We're going to make these two equal to each other. So in black, it would be this part on this side, which is going to be mu static friction, coefficient of static friction, times mg cosine theta is equal to this side of the equation, mg sine theta, right? Just so happens if you divide both sides, it will be mu equals to tangent theta. So this is the first part. So it has to be either this one or this one, right? Second thing is, well, you know, the reaction force must be equal to this one, right? So it cannot be sine, it must be this. Okay? Next, it says An object released from rest in the gravitational field of the Earth. Air resistance negligible. How far does the object move in the 4th second of its motion? So let's make a table. And let's make the table for time, one side, right? And let's make this the position height, right? And it says it is released from rest, so it's dropped. So 0, 0. That's where it starts. After 1 second, after 1 second, how far does it drop? Well, it's going to be 1/2 AT squared, right? This is assuming that that A is equal to -10 meters per second squared. Another thing is they're going to ignore this sign, right? Because they want the distance that it goes down, not the vector. So the sign is irrelevant. So at the 1st second, it's going to go down 5 meters, right? After 2 seconds, it's going to go down. So let's just write it down. So it's going to be 10, 2, 4 times 10. No, so this cancels out, doesn't it? Squared. So 20, right? After 3 seconds, 1/2, 10, 3 squared. So 1/2 times 10 is always 5, right? 5, this is 9, this is 45, right? You keep doing this, you go 4, and we go to 5. So let's reduce this to 4 times 4 squared equals 80, and 5 times 5 squared, 125, right? You might notice something that in the 4th second it goes to 80 meters, but 80 meters is not one of the answers, right? So what is happening? Well, it says during the 4th second, not how far does it go from 0 to 4. What it wants to know is how far it goes from 4 to 5, right? Because this is the 1st second, from 0 to 1. The 2nd second is from 1 to 2. The 3rd second is from 0 to 1, 1st second, 2nd second, 3rd second, 4th second, right? So I guess 1st, 2nd, 3rd, 4th, how much it goes from here to here, which is going to be 35. Probably, yeah. Right? Yeah. Okay. Projectile motion is fired horizontally from the top of the cliff. The projectile hits the ground 4 seconds later at a distance of 2 kilometers from the base of the cliff. What is the height of the cliff? Well, again, you dropped something. It took 4 seconds to drop. The horizontal velocity doesn't matter. And actually, the horizontal distance, it's bait. it's unusable information for this. After 4 seconds, you know, well, we did the table here, right? It's going to go down 80 meters. So the table was useful. This table doesn't ever change on Earth, right? As long as the acceleration is 10 meters per second squared, this table will always remain the same. Let's say a boy throws a ball horizontally at a speed of 15 meters per second from the top of a cliff. That is 80 meters above the surface of the sea. Air resistance is negligible. What is the distance from the bottom of the cliff to the point where the ball lands in the sea? Well, 80 meters, again, if it drops 80 meters, it dropped for 4 seconds, right? So you can see, like, this table, knowing what this table is, what it looks like, it's very useful for the test, basically. You don't have to memorize it. You can probably just calculate on your own anyways. Right? So for 4 seconds, how far would it go in 4 seconds? Well, you know this velocity is horizontal. We know the time it takes to get there. So it's going to be 4 times 15 is 60. And remember, this 80 meters is the time it takes to go down 80 meters. completely independent from how it goes horizontally.
Even though it's fired horizontally.
Yes. So, and this brings me to today's topic, two-dimensional motion.